Well, hello, Algebra 2 class. I trust that everything went well in 6.5 for you. Today we're going to jump into 6.6, talking about the factoring of polynomials. So just to do a quick warm-up here, this first one says factor x squared minus 3x plus 2. So again, we would just set this up as two binomials. We would have an x and an x. And we would think, what is it that multiplies together to make a positive 2 that can add together to make a negative 3? And in this case, you should be thinking about negative 2 and negative 1. If we FOIL this out, we'll get this answer. And this next one, solve x squared plus 2x, or plus 2 equals 3x. We would first of all subtract that 3x over to the other side. And then that would be set equal to 0. Now note, once I do that, I have exactly the same factoring that we had up above, with the exception this time that it's set equal to 0. So we just have to ask ourselves, what makes this part equal 0 and what makes this part equal 0? Which is obviously going to be 2 and 1. And then on the last one here, find the zeros of f of x equals x squared minus 3x plus 2. Well, we've just found those. They are 1 and 2. All right, so we're going to talk about just general forms of equations. First of all, the linear function, which you guys are already familiar with, is just f of x equals mx plus b, where m is the slope and b is the y-intercept. In the quadratic function, we have f of x equals ax squared plus bx plus c, which you've also already seen. Now, a function that can be written in the form p of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on and so forth, until we eventually get to a1x plus a0 is a polynomial function. So each of these a's are coefficients, and then each of these powers of x are running down from some number down eventually to where it gets to just x to the first, and then eventually just a constant itself. Now, the remainder theorem says if a polynomial p of x is divided by a binomial x minus a, the remainder is p of a. In other words, if we divide a binomial, divide a polynomial by this binomial x minus a, the a value, when we divide this, the remainder of, when we plug in that a value into the equation itself, is the remainder of the division. This becomes important. It's an important principle. Will allow us to figure out how to factor some difficult polynomials otherwise. Let me show you how. Example 1. It says find the remainder when x to the fourth minus 3x cubed minus x squared plus 2x plus 7 is divided by x minus 1. So we can actually go about doing the entire division, long division, or we can do it, since we have it in this form where it's x minus or plus some constant, we could go ahead and do synthetic division on this problem, which you guys just learned last time with me. But let's go ahead and use this theorem that we just learned. We can plug in the value. Notice that it's just 1. You do the opposite sign of whatever is in front of this constant. So if it's a negative 1, you're going to put p of 1. If this happened to be x plus 1, you would put a negative 1 in for here. But instead, we'll just plug in 1. So it'll be 1 to the fourth minus 6 times 1 to the third minus 1 squared plus 2 times 1 plus 7. Well, the 1 to the fourth is just 1. This becomes negative 6. This becomes negative 1. This becomes plus 2. And this becomes plus 7. And when we do that, we get 3. So what the theorem tells us is that whatever that answer is, this 3, that is going to be the remainder whenever I divide this polynomial by this binomial. So without even having to do the division, we know what the remainder will be. We just plug in the opposite sign of this part into the actual equation, and whatever answer we get out, that is the remainder if we were to do the entire division. Now, the factor theorem says a binomial x minus a is a factor of a polynomial p of x if and only if p of a equals 0. In other words, from that previous thing, if we know that whenever we take a binomial like this and we take the opposite sign of whatever this part is and we plug it into the actual original polynomial, if we get the answer of 0, that means that the remainder is 0. And if the remainder is 0, that's by definition a case in which it's an actual factor. It factored cleanly into another thing. So if we plug in that value and we get a 0, we know then the x minus a is a factor of the polynomial. So it says here, determine whether x plus 2 is a factor of p of x equals x to the fourth plus 2x cubed plus 2x squared plus 3x minus 2. So all we need to do is figure out if p of negative 2, note here that the sign of the value of this is always the opposite of whatever the sign is on this guy. So if it's x plus 2, we put in a minus 2. So we plug in minus 2 into this whole thing. If we get out an answer of 0 at the end, if the remainder is 0, that means that this entire binomial is a factor of this polynomial. So let's try it out. If we do p of negative 2, we just plug in negative 2 wherever we see x. And after you've done the algebra here, we get 16 minus 16 would be 0. 8 minus 6 minus 2, that would be also 0. So 0 plus 0 is 0. And since it's 0, the remainder is 0, which means that the original binomial, x plus 2, is a factor of the polynomial. So the rational root theorem generates a list of all possible rational roots of a polynomial function with integral coefficients. This is what that root theorem looks like. The most important part here is that we're going to be looking at is this p divided by q is a rational zero root in the simplest form. But instead of just looking at these words, I want to show you an example because I think it will become clear what we're doing with the rational root theorem if you see some examples. So let's look at example 3. It says factor p of x equals x cubed minus 3x squared plus 5x minus 6. So the p and q are the coefficients that are found in front of this x, the leading term in the polynomial, and then the last term in the polynomial, the constant. So the factors of 6, we have to ask what values of numbers can give me a negative 6. Well, it could be like positive 1 and negative 6, or positive 6 and negative 1. It could be any combination of 2 and 3, 1 being positive, 1 being negative. And so here are our possible factors. It's 1, 2, 3, and 6, positives and negatives depending on what's going on. Then we can ask what are the factors of 1. That would be, again, what's implied in front of the x cubed here. And so it's just positive or negative 1, because you take negative 1 times negative 1 and get 1, or 1 times 1 and get 1. So now, all that we have to do is look at the possible zeros, which are all found from just taking p divided by q. So we take whatever is the constant at the end of the polynomial, and we divide it by potential factors of the front of the polynomial. And when we do that, because it's just plus and minus 1, we just result with the same list as the factors of p, because we're just dividing by positive or negative 1, and it's either making them positive or negative depending on the combination that's there. So, in other words, the only things we need to check are these values. These are the only possible solutions for factoring of this polynomial. So, we can try it out. If we put in a 1, let's just test 1. So notice here we have a possible number of testings of 1, 2, 3, 4, 5, 6, 7, 8, right? We have 8 numbers here because it's positive and negative 1, positive, negative 2, positive, negative 3, positive, negative 6. So we can plug in these one at a time into this polynomial and see what we get. If we plug in p of 1, we'll get 1 minus 3 plus 5 minus 6. So 1 minus 3 would be negative 2, plus 5 would be 3. 3 minus 6 is a negative 3. So obviously, since we got an answer other than 0, that means that this cannot be a factor. So remember, then we take the opposite sign of whatever it is that we put in here, and we can say that x minus 1 is not a factor of this because the answer we got when we plugged it into the polynomial was not 0. If we plug in p of negative 1, we'll get the answer of negative 15. Well, negative 15 is also not 0. So that means, again, the opposite sign of the negative would be positive. So here, x plus 1, that is not a factor either. Well, let's try 2. Well, if we plug in 2, we'll get 2 cubed is 8. Minus, it'd be 2 squared is 4, times 3 is 12. 2 times 5 is 10, and then here minus 6. So we'd have 8 plus 10 is 18, minus 12 is 6. 6 minus 6 is 0. So that gives me a 0. And since that answer is 0, that means the remainder would be 0. So again, we flip the sign on whatever we put here, and we say x minus 2 is a factor of p of x. So since we know it's a factor of p of x, we can now go ahead and do our synthetic division. Now, the beauty of doing it this way, guys, is you're not doing synthetic division multiple times with things that we don't know if it's a root or not. What we want to do is plug in that value, see if we get a 0. If we do, we know it's now a root. And now we do the synthetic division with the thing that we know will give us a 0 at the end. So we're not doing extra work than we need to. So remember, if we're setting it up for x minus 2, we do the opposite of the sign when we put it in the box here for synthetic division. And then we look at all of the coefficients in the original polynomial, and we're going to list those here. So it's 1, negative 3, 5, negative 6. Now remember how we go about doing this. We bring down our 1. We then multiply this 1 times our number in the box, which would be 2, and we put that number here. We then add down. We get negative 3 plus 2 is a negative 1. We then, again, multiply that by the 2 up in the box, so we'll get negative 2. We then add down. We'll get 3. 3 times the 2 is 6. We add down. We get 0, which is exactly what we said we were going to get when we plugged in 2 into the original polynomial, which told us we knew it was a root. Okay, so now what this means is now we can translate each of these values into their corresponding values for the rest of the factor. So we know one of the factors is x minus 2 because that's what we were basing all of this on. And then what's left is, remember, we can work our way backward through this. This becomes just the constant. This we put an x by, and this we put an x squared by. Remember, just going to work our way up the powers of x going from right to left. And so what we're left with here is x squared minus x plus 3. The quotient, such as x squared minus x plus 3 in the previous example of a polynomial divided by one of its binomial factors, is called the depressed polynomial. Consider 2x cubed plus x squared minus 1. So here we could rewrite this as p of x equals x plus 1 times 2x minus 1 times x plus 1. Since x plus 1 is twice a factor of the polynomial, we call negative 1 then a double root of the function. So in this case, the root negative 1 works there, but it also works here. This one in the middle, notice if we were solving for 0 here, it would be 1/2, right? X equals 1/2. But in these cases, it's x equals negative 1. But it happens twice, so it's called a double root. So we still have 3 roots. It's just that one of them is a double root, and the other one here is just a single root. It's 1/2. So now I just want to mention a couple of special factoring patterns that you need to be familiar with, and I'll show you a couple of examples of using them. This first one is just the difference of squares, one that you should already know. Whenever we have a squared expression subtracted from another squared expression, we can rewrite that as a plus b times a minus b. Now, if we have them, and instead of subtracted, added, the only difference here is that we get the imaginary numbers here of plus and minus bi. Remember, because you'll get a square root of negative 1. But what about when we have a cubed situation? Well, when we have a cubed plus b cubed, here's the pattern that we can write that as. A plus b times the quantity a squared minus ab plus b squared. And then the difference of cubes looks like this. A minus b times the quantity a squared plus ab plus b squared. So notice what changes here. When we have the addition of 2 cubes, the first thing is a positive, but when we get to the ab in the middle of this expression, it's a negative. But when we have a negative, a difference of cubes, the first expression is negative, the second one is positive. So you might want to look at that and try to kind of commit that to memory, because these are a couple of useful factoring patterns that will come up from time to time. So let's look at this example. Factor x cubed minus 64. So I've placed here for our help the difference of cubes formula that we had previously. Now note, whenever we have a difference of cubes, we need to break down each part into their non-cubed self. So in order to do that here, we need to notice that x cubed minus 64 is the same thing as writing x cubed minus 4 cubed. Right? So now we have x cubed minus 4 cubed. So now we have the form of a and b, each of them being cubed, and there's a difference between them. So now we just plug in x for wherever there is an a, and we plug in the 4 for wherever there is a b. So it looks like this. X minus 4 times x squared plus x times 4 plus 4 squared. And after having done that work, we get x minus 4 times the quantity x squared plus 4x plus 16. What about this guy? He looks even worse, doesn't he? But he's actually not that bad once you recognize that this is a cube and so is this a cube. Well, how is this a cube? In other words, ask yourself, what quantity is being cubed there? And so we can rewrite this first one as the quantity 2c cubed, right? Because 2 times 2 times 2 is 8. So 2c is now going to be my a. And my b, I have to think about this guy and think what's being cubed here. Well, 3 times 3 times 3 is 27. But what times itself 3 times gets me d to the 6th? Well, it would be d squared. Because remember, whenever we raise an exponent to another exponent, we multiply them together. So here, we can rewrite this with 2c being my a and 3d being my b. So then I just have to put these in to this equation in according fashion. So 2c goes wherever there was an a, and 3d squared goes wherever there is a b. And then as you multiply that out, we get 2c plus 3d squared times the quantity 4c squared minus 6cd squared plus 9d to the 4th. Now, some polynomials can be rewritten as quadratics and factored using the previous methods. Factoring is a common factor from several groups of terms may reveal a common binomial factor. For example, here, we have x to the 4th minus 5x squared plus 4. Again, this looks kind of messy right here. That is until you recognize that really all this is if we rewrite this as x squared being squared and this x squared in the middle just being in the place of this kind of then looks like the form x squared minus 5x plus 4. And I'm almost certain you guys can factor that guy, right? This would just be x minus 4 times x minus 1. Right, you could FOIL that out and you'll see you get the same answer. So now all we do is we place an x squared wherever there is an x in this factoring problem. So it just becomes x squared minus 4 times x squared minus 1. Now at this point, this becomes all the more helpful, right? Because what are these? These are differences of squares. X squared is a square, right? A perfect square. And 4 is a square. So is 1 a square. So we can rewrite both of these as x plus 2, x minus 2. That's for the x squared minus 4. And the other one, x plus 1, x minus 1 for the x squared minus 1. So this just ends up being a product of two differences of squares, which we can further delineate this way. Okay, what about this one? Well, on this guy, we have to remember one other little trick that we can do with problems like these, and that is the trick of being able to group them in different ways and factor out things from the groupings. In this case, notice that we can take from the first two, we can take out a common factor of x squared, leaving behind an x minus 5. And in the second two, we can take out a common factor of negative 9 and be left with inside here x times x minus 5. Notice that these two now are the same. And if those two are the same, we can rewrite the whole problem as x minus 5 times the quantity, whatever is here, plus whatever is here. So x squared minus 9. But notice what this is. It's a difference of squares again. X squared, and this would be 3 squared. So we can rewrite that as x plus 3 times x minus 3. All right, so you're going to get a lot of practice just factoring polynomials in this section. Again, if there's anything you didn't understand, you can rewatch this video, go over it again, slow it down a little bit, read through section 6.6, as it does a pretty good job of explaining it as well. And then I want you to do problems 2 through 34, and then 40 through 48. Just do the evens on all of those, as is our normal custom. That's found on pages 265 and 266. Please let me know, guys, if you have any troubles. Reach out to me. I'd love to help if I can in any way. Otherwise, hope everything's going really well for this distance learning week. Hope you guys are safe and feeling well. I'll see you guys soon.